Assalamualaikum and hello everyone. We are from Group 9 and today we will be critiquing the article Heavy Metal Removal from Produced Water Using Waste Material, a comparative study published in Water in 2025 by Bansal, Mortula and Al-Asheh.
The objective of this article is to compare 7 types of waste material absorbent to remove heavy metals from produced water. The result is the best absorbent is dead seed ash, while the least effective absorbent is pistachio shells and gypsum.
Alright, so moving on to our critique of the paper's foundation as let's look at the clarity of research question. One of the strongest aspects of this study is that the authors didn't leave the reader guessing. They explicitly defined a threefold objective right in the introduction, which set a very clear roadmap for their methodology. Right. So first, they want to evaluate and compare the removal efficiency of 7 specific agro-industrial and construction waste. So, what makes this objective strong is its measurable nature. They aren't just asking, do this material work? They are systematically pitting materials like dead seed ash against gypsum and mandarin peels under identical multi-melter condition to see exactly how they stack up against each other, right? So, secondly, they aim to examine how specific material characteristics like surface morphology, functional groups, and crystallinity, right? How can they influence the absorption process? Okay, so this is where the study digs into a fundamental science. Instead of just stopping at the removal percentage, these objectives promise that they explain the why behind the data. It tells us that they plan to use analytical tools like SEM and EDX to prove that surface chemistry and physical structure are what actually drive the heavy metal capture. And the last is they want to assess the practical feasibility as sustainable and low-cost adsorbents for produced water treatment. So this bridges the gap between lab-scale theory and real-world industrial applications. It answers that the ultimate so what of the research that frames the entire study around the principles of a circular economy that turns the industrial waste into a solution for industry pollution. So, because to conclude, because these three objectives were so clearly laid out, it made evaluating the rest of the methods and conclusion incredibly straightforward.
So, for appropriateness of methods, the methods are largely appropriate. Using a standardized synthetic produced water allow for control comparison across 7 materials. The SEM, EDX, and SRD combination directly support the study goal of linking material structure to performance. However, there are limitations. No kinetic study was done to confirm true equilibrium at 18 hours. Only 2 dosages were tested, and the sample size was just 2 replicates per condition, which limit the statistical confidence.
Okay, next is regarding validity and the interpretation of data. The study is strengthened by control condition, blend samples and physical surface analysis like SEM and SRD. However, key inconsistencies weaken the reliability. Dosage report conflict between the text and abstract. Measurement method switch between UVVIS and AAS. The text incorrectly claiming activated carbon had low lead removal, despite the table 2 had shown that it is 98% efficiency. Particularly, this data discrepancies hinder reproducibility. Okay, right now we are moving to limitations. While the authors slightly note potential metal interference from raw materials and suggest reusability studies, critical gaps still remain. The test used synthetic water rather than real petroleum wastewater. Runs were only in duplicate without statistical testing, and kinetics and reusability and safe disposal were ignored. Overall, while promising, real-world wastewater and continuous flow testing are essential before industrial application.
Despite these limitations, the findings are significant. Produced water treatment is a real and a large-scale environmental problem. and using a low-cost agricultural waste to treat it supports circular economy goal. The study also fills a draining gap by comparing 7 materials side by side under the same condition, which is rare in this field.
Next, let's look at the ethical side of this research. The good news is this study has no negative ethical issues. There is no harm to people, and there are no conflicts of interest. Instead, this research strongly focuses on protecting the environment and keeping the public safe. All right, next, let's look at the ethical side of this research. The good news is this study has no negative ethical issues. There is no harm to people, there is no conflict of interest. Instead, this research strongly focuses on protecting the environment and keeping the public safe. The authors are helping to solve a major health problem. They found a way to stop dangerous heavy metals like lead and zinc from building up in our water system. This is incredibly important because these toxins are known to cause serious health issues in humans. So, additionally, this study promotes green engineering by refusing leftover waste like dead beets, fruit peels, and gypsum boards instead of using expensive manufactured chemicals. All right. So, the researchers are helping this planet in two ways. They are cleaning up the toxic wastewater and they are reducing the amount of trash sent to the landfills. So, this ensures that the water treatment process itself doesn't create any new pollutions.
To conclude our critique, the article succeeds to introduce and compare the efficiency of the 7 waste materials to remove heavy metals. Also, the article proves that the feasibility of using the 7 materials to remove heavy water, but it varies in efficiencies. Some critiques to improve research accuracy is the use of synthetic water instead of real industrial produced water. Also, this research also used very low number of samples and inconsistent dosage amount at different stages of the experiment. That is all from us. Thank you.